Hello, everyone. My name is Dimitris Katsios, and this is Deep Learning with Python, chapter 11 today. So chapter 11 actually quite big, huge, and I thought to break it in two parts. So today we'll do the first part, tomorrow, next week we will do the second part, and it's still a big one, so it will take some time. Now, this week we will see deep learning for text, so completely new thing. And here are the chapter contents. So we will do the first two today and the second two the next week. So what we are going to see is pre-processing text data for machine learning applications. So we saw something like text applications before, but not with the raw input. We saw how to treat it when it's already tokenized, as we will learn today. And the second thing is one approach, the bag of words approach, and the sequence-to-sequence modeling approach for text processing. So these are two of the things that we will see today. And let's start. So natural language processing, the bird's eye view. And what it is, NLP tasks. So these are some of the tasks that you usually do when you deal with text. For example, you might do text classification. So a question like, what's the topic of this text is in the text classification category. If you ask something like, does the text contain abuse, for example, if you have tweets or something like this, or some comments, then we have something like content filtering. If you are interested in something like, does this text sound positive or negative? This is sentiment analysis. This is very important, for example, for movie reviews, or I mean, if you have huge content and you don't want to do it manually, these techniques are usually used. Another one could be, what should be the next words in this incomplete sentence? So this is generally the when you try to generate text. We will see actually in the next chapter how to generate text. And this is generally the language model. So how you can model the language as an entity, and then how you can produce the next words. Of course, translation. So how would you say this in German or any other language? And finally, we have the summarization. So if you have a big text and you want to have a summary, this could also be another application. And of course, there are many more. So regarding the history, very shortly, before 90s, there were very few applications. Between 90s and 2010, we had mostly some applications with decision trees, with logistic regression, and all the techniques were based on feature engineering. So the data were very heavily feature engineered, different structures were used. After 2015 up to 2017, we used mostly recurrent models, recurrent networks. LSTM is the most commonly used, and actually Keras was the first framework that open sourced something in this category, in this family, that was easy to use, easy to implement just online. Before that, it was quite difficult just to write the kernels and everything. And the very important for natural languages, we have in 2017 up to present actually the transformer architecture, which is the one that we will see next week. So let's move on. We will start with an example, and then during the example we will explain things like we do most of the time. So we have the thing with text is that it's not numbers. So we know that for deep learning, we have the different layers and we have the functions. So all these have to do with tensors, and tensors have to be numerical data. So the pre-processing part for the language is even heavier, even bigger than the images that we saw. So for images, it was mostly some normalization, some resizing, and that would be all. For language, it's a bit more complicated. So we have text, and then we want to transform it to some numeric tensor. And this whole process is called vectorization. So let's see what are the stages. I mean, it can be more complicated than this, but let's see the standard, the most usual stages. So first of all, we have standardization. So standardization is about the text itself, how we can standardize. For example, if we have capital and lowercase, we want everything lowercase, let's say in some example. Or we want to remove punctuation, we want to remove the comma, the full stop, the exclamation mark. And of course, this part, it depends on what we want to do. For example, in some cases, we might actually want to keep the exclamation marks because we want to do sentimental analysis. Then, after we have standardized the text, we have the tokenization. So tokenization is when we take the sentence and we split it to units, to specific tokens. So these tokens can be characters, not now, mostly in the past. It can be words, single words, or it can be group of words, as we will see today. And then after we have the tokenization, we want to take this token and transform it to some numerical vector. For example, we can do indexing. And let's see here an example. We have the text, let's say this sentence. Then we do standardization. In this case, we transform this to lowercase and we remove the full stop. And then we take the tokens. In this case, each word will be one token. Then we transform these tokens to numbers. So these numbers is just like, I don't know, imagine a dictionary with one number for each word. So more or less just integers. And then we want to make it a vector. So we will not feed, of course, the number 3, we will feed a vector. In this case, we see an example of one-hot encoding like we have seen in the past. And today we will learn about the embeddings, which is a much more powerful way to vectorize it. So let's continue. First of all, the text standardization. Let's see these two sentences. So these sentences, the first two sentences, seem quite similar to each other. However, if you actually want to treat them as information, these are not, I mean, here you have a full stop, here you have this symbol, you have a lowercase, uppercase. So here you have, for example, E with this punctuation mark. Here you have the standard Latin E. So what you want is to erase the encoding differences like this one that you don't want the model to deal with. So if your model, for some reason, doesn't care, you don't want the model to care about the difference between Mexico and Mexico, then you can just transform this to the same words, Mexico here and Mexico lowercase here. So this is one example. Another example, it would be that also this technique actually is not exclusive for machine learning like we do here. It was used even before, for example, for search engines. The first step was whatever you write to standardize it. So here we see these two sentences is how they would be after this standardization, and you see that now they look way more similar to each other. Here, for example, we have also removed this symbol, we have removed these symbols, and this is how we standardize it. Next step, after we have standardized words, we have the tokenization. Again, for tokenization, we have the, it can be word level. For example, we have everything that is, since we have removed the punctuation marks, we have only spaces, and we can take whatever is separated by spaces. So we treat it as one token, one word. Or we can have n-grams. So n-gram tokenization was actually very popular in the past, and it's a way to artificially inject a small amount of local word order information to the model. So what are the n-grams? The idea with the n-grams, for example, 2 grams, is that instead of having one token to be one word, it can be one word or 2 words if we have 2 grams. Or if we have 3 grams, we can have 1, 2, or 3 words, one token. So for example, we will see an example later, but the idea is that the cat can be one token by itself, or he was can be one token instead of 2 tokens. And there is, of course, the character level tokenization, where each character can be its own token. This is if you want, for example, to have a simplistic approach to generate, I don't know, names of dinosaurs, for example. And the text processing model. So apart from this, we have the 2 main categories on how to deal with whatever we tokenize. And there are 2 main categories, the sequence models, which is word level tokenization, and the bag of word models, which is usually n-gram tokenization. So based on which model we will use, we apply the appropriate tokenization. And we will explain what are the sequence and what are the bag of words category of models. So after that, after we have the tokens, what we want is to transform them to numbers. And the simple way would be, first of all, to have the vocabulary indexing. So we take the words, we have each token, and we encode each token into a numerical representation. So let's see here. What we can, in order to do this, what we can do is to build an index of all the terms found in the training data. So this data, this corpus, is called the vocabulary. Sometimes we don't use all the words. So there are many cases where you have words that appear once, maybe twice in a corpus of, I don't know, hundreds of thousands of sentences. And in this case, well, you don't want to have a huge vocabulary. And that's why sometimes you crop it to the most 20,000, for example, or 30,000 most common words. But either way, either you crop it or not, this will be your corpus, your vocabulary. And then what you're going to do is to assign a unique integer to each entry to the vocabulary, to each token of the vocabulary. And here is a simple way to do it. Of course, this is not very efficient. But the idea is that we have an empty dictionary, and then for each text in the dataset, text will be, for example, the sentence or the paragraph. First of all, we standardize it, then we tokenize it, and then for each token, again, it could be a single character, it can be a single word, or it can be n-gram. We take this token, and if it's not in the vocabulary, you add it and you assign the next integer. And then the next thing you want to do is to encode it to a vector. So this is integer, and then you take the token, whatever integer it is, and you produce a vector. For example, this is the one hot. You take the, you make a zeros array, and then you just assign one to the position of the specific token. Again, this is, of course, not very efficient, just for explaining how tokenization and how one-hot encoding works. By the way, there are two things here. Let me see if I have another one. Yeah. So there are two indices that are usually occupied for very specific reasons. We didn't see it before, but the idea is that the index 0 and the index 1 are not used for tokens, for words. So we have the out of vocabulary index, which is usually the index 1, and the abbreviation is OV. And this means that you have, here is a word that I didn't recognize. So for example, if we have cropped the whole vocabulary to 20,000 words, there will be some words that are outside the vocabulary. In these cases, we assign the index 1. And there is another index that is for specific cases, it's index 0. And index 0 is used for masking, is used in order to make the each sentence, whatever it will be, the representation, the same size. So let's say that you want to have a batch that has, I don't know, 64 sentences, and then you want each sentence necessarily has to be the same size. So in this case, you want to use these, for example, zeros, to make them both, I don't know, 6 or 5 here. So the length 5. And in order to achieve this, you have to append some zeros in order to have the maximum size every time. So 0 and 1, we don't use them for specific tokens like this. We use it for these cases. Now, of course, what we saw before could work, but it's not efficient. And this is why we will not use this code. We will use some that is already implemented in Keras. But before this, let's see how this would look like if we wanted to implement it by yourself. So let's say that we want to have the vectorizer class that takes the text and it vectorizes the text. First of all, we have to define specific classes. For example, standardize, we have any text that we take, we make it lower, and this is in order to remove any punctuation symbol. So string for every character that is in these characters, you just replace it with nothing. So you just use this empty string. After you have this standardization, then you have the tokenization. So here again, first of all, you standardize the text using this, and then you split it based on the spaces. Pretty simple, same as we described before. Now, after the standardization and the tokenization, you want to make your vocabulary. Again, we keep this 0 for the empty string, and we have 1 for the unknown word. So we start with these 2 in the vocabulary, and then, as we saw before, first of all, we standardize the text, we tokenize the text, and for each token, if it's not in the vocabulary, we assign the next value, more or less, again, what we saw before. And we also create the inverse vocabulary that we will use in order to decode the encoded sentences, which is just the keys become values. And then we have the 2 methods, the encode method and the decode method. So the encode method takes any text, any sentence. We standardize, tokenize, and then we add it, we call it on the vocabulary that we have already made before from the corpus. And if the word is not in the vocabulary, we return 1. So this is encoding, and the decoding is that we just take the inverse vocabulary, and for its integer, for its index, we return the word, and if the word is not there, we return unknown. We instantiate the vectorizer, and then we have here a very simplistic example. We have a list of 3 sentences, and we make the vocabulary based on this very small corpus. So let's create this. And then this is how this would work. And this is more or less how we will work with the actual Keras layer. So we have a new sentence, a test sentence. And the first thing we're going to do is to vectorize it. So we encode this sentence. Since we have already made the vocabulary, we can just encode it, and we can get the encoded sentence. So this sentence is just indices for each token from the vocabulary, okay? And then if we want to decode it, we just call decode, and it should be more or less what was before, but this time it will be standardized. So we will not have the comma, this will be lowercase, and of course for words that are not like the word still that was not in the original corpus, when we created the vocabulary, we have the unknown. So this is more or less how this works. Now we are going to see how, because it's again not very performant, we are going to use the Keras version, which is called text vectorization. So let's see how text vectorization actually works. So it's quite simple. All the code that we wrote is more or less this thing. We just import text vectorization, and we instantiate it, and we have the output mode. So the output mode can be different things. In this case, we want integers, which means that each token will be represented as 1 integer. In the next, we will see more complicated, but keep this for the moment. So let's see, the default settings for this is more or less what we did before. So in order to standardize, this class uses the lowercase, so they convert everything to lowercase, and it removes punctuation characters, the same thing as we did before. Of course, if you want something different, for example, if you don't want to remove the specific characters or specific symbols, or you want to apply something different, like the capitalization, if the whole word is capitalized, you want to keep it because of segmental analysis or whatever, then you can provide custom functions too, and we will see how to do this. And for tokenization, again, the default is split on white space, but of course there is an engram and many other things. So this is how you can customize it in case you want something different. Let's say that we want, well, here it does more or less what we said, lowercase, and replace these symbols, the punctuation symbols. But the idea is that you can do this and you can add other things here. And the idea is that, of course, you have to use TensorFlow functions. All the functionality inside here should be TensorFlow so that it can work in the layer. But TensorFlow in strings has many things, so I guess many of the things that you will want to do is already here. This is how you can create a custom standardization function. And for the split function, again, you can use this or you can use something more complicated. And the way you pass them is, again, pretty simple. For standardize the function you want, or for split the function you want. And of course, you don't have to write the decorator here, the TF function, because it will be part of the layer, so it will be compiled either way. So let's run this one. Yeah, we import TensorFlow, that's why it takes some time. What? Ah, we didn't run the, sorry, I have to run this one first. Okay, and now we can run. Okay, so let's continue. So to index the vocabulary of the corpus, you have to call the adapt method. So before we called something like make vocabulary, create a vocabulary, something like this. Now the default way to do it is to call adapt. So let's see how this would work. We have the same sentences as before, and then we just get our layer and we call adapt on this dataset. And now it has created the vocabulary, the internal vocabulary. So the entries, one difference is that here the entries on the vocabulary list are sorted by frequency, which means that the most frequent word will be in the vocabulary. If we want to crop it to maximum, I don't know, 20,000, as I said before, or here something smaller, then we will keep by default the most common words, which is very useful. So with real world examples, for example, the word the or ea or I or these words will come first in the vocabulary because it's actually just a list. Let's display how we can use the vocabulary. So first of all, this is the vocabulary. It's again just a list. We have this, we have the unknown, and then we have the words in order of how common they appear. And this is how we can encode and decode. So we have this vocabulary, and let's say we have this the same test sentence as before, and we just call this object, this text vectorization on the sentence. We don't have to call a specific method, and this returns the encoding sentence. So let's see this sentence. And like before, we just have numbers here. It's a tensor, of course, TensorFlow tensor. And this is how we decode. So in order to decode, we have the inverse vocab, which is just we take the list and we inverse it to make the dictionary. And we call the same thing as we did before in order to decode the sentence. And again, as before, we have this standardized, so lowercase, we have unknown here. And of course, this one is much faster and optimized. So this is what we are going to use from now on. Now, a different thing regarding the approaches. As I mentioned before, there are two approaches for the representation of the words. You can either represent the words of the sentence as a set or as a sequence. And let's demonstrate it using a dataset that we have already used before, using the IMDb dataset. So let's see the approaches. The simple approach would be that the text, whatever we have, is just a set of words, which is called bag of words models. Another approach would be some that the order matters. So we take the text and we break it to times, the same way we used time steps before. Now we will use the words as time steps. And this is used for the recurrent models. And there is a hybrid method where it's order agnostic, but still we have some information regarding the position. And this will be the transformer for next time. Let's take the IMDb movie reviews datasets that I mentioned before. We have already seen this. So this time, let's see the raw data, not the integers as we did before. So this is the structure. We have this, here is the directory with the dataset. We have the test, train, and val directories. So let's take the train. Inside the train, you can see that there are some things. We are interested mostly in the pos and the neg, and each one of them has just texts. So text files like this, and we have many in pos and many in neg, both for test, train, and validation, of course. So this is more or less the structure. And I cannot, okay, sorry for that. So let's see what it looks like. So if we get a random text from the positive, for example, it looks like this. So I first saw this back in the early 90s, etc., etc. And we have some tokens like this, but it's not important. So this is more or less what these texts look like. It's a review for a specific movie. Now, let's create the actual the actual data set. So we have again three: the train data set, the validation data set, and the test data set. And the idea is that we call this text data set from directory. We pass the directory, and it finds the subdirectories, and for each subdirectory, it creates a class, the positive and the negative. And of course, we can define the batch size here. So we see that we have 20,000 files in two classes for training, etc., for the validation and the test set. Now let's see what they look like. So what do these samples in the batches look like? So we just take one iteration, the inputs and the targets, and we print this information. So the shape will be 32. 32 because the batch size was 32, but you see that we don't have any information in the tensor regarding the size because it's a string. So the D type, the data type for this TensorFlow tensor is string. And regarding the target, it's 32 numbers of type integer 32. And this is what it looks like. So the input looks like, again, text. And the target looks like just a number. In this case, 1 for the positive ones. So let's see how we can pre-process so that instead of text, we have some numbers, some arrays. First of all, we will see the bag of words approach, which is, and we will see the very simple one, which is Unigram. So one word, one token, which means that this sentence, the cat sat on the mat, will become a set. Be careful, not a list, it's just a set of separate tokens, one for each word. So and then we will take this, we will make the vocabulary, and then we can encode it as a multi-hot vector. We will see how. And here we have the number of the words in the vocabulary for the dimensions, and it will be binary for the multi-hot vector. It will be 0 if the specific token doesn't exist in this sentence, or 1 if it does exist. So we will have, let's say, a vocabulary of 20,000 words, so 20,000 zeros and ones regarding of if these words exist or not in the example sentence. Let's see how we can do this with the text vectorization that we saw before. So we create the text vectorization and we define the maximum tokens. I explained before why we want to crop it to a specific number, because otherwise it would be many hundreds of thousands. And the output mode now, it will not be integer, it will be multi-hot. So first of all, we have to do this little thingy here because we want to use this to create the corpus, the vocabulary, only on text, not the target. So for every target and for every input and target, we just keep the input. So this is the text-only train dataset. And then we adapt the text vectorization. We call adapt on this only the sentences, only the text. And after we have adapted this one, we can use the train dataset to map. So remember, we have seen the dot map method before, and for each X inputs and Y targets, we replace X with the text vectorization, the output, the encoding of the text vectorization. And of course, we do this for the training, the validation, and the test. So this is how we will pre-process more or less the data. Again, we create it here, we adapt it only on the train data. And then using this, and with multi-hot, and using this, we created these datasets that will output now multi-hot vectors and not text as before. So let's see now what they will look like. Where did this go? Inspected, yeah, inspected, we are here. I already, yeah. So this is what it will look like. We take now from the binary 1 gram train dataset, again, the inputs and the targets, but you see this time we have 32 by 20,000. This is float 32. And this is 20,000 because this is the size of the vocabulary. And in here, as you can see, it's ones and zeros. And the target remains just the same as before. We didn't change the target. So this is the pre-processing. Now let's move to the model. So for the model, we will have a function that returns a model because we will call it again and again. So we define the get model, what is the maximum number of tokens, which will be, of course, the input shape, the maximum tokens. And we define one hidden dimension, which will be for the dense layer. So very simple structure here. We have the inputs, we have a dense layer on this with 16 outputs, activation ReLU, we apply dropout, and then we have one dense layer with one output. Again, it's one because it's either positive or negative. So either 0 or 1. So we output 1 with sigmoid. We build the model, we compile the model, nothing new here. It's just things we have already seen. So again, 2 layers for this model. It's a very simplistic model, and yet we will see that it produces not that bad results. So training and testing the binary Unigram model. It's Unigram because we will see the bigram next. Of course, I have already trained this, so because it takes some time. Actually, the next ones take way more time. And here is the test accuracy, and we have 88.9% accuracy. So the dataset is balanced more or less, which means that with a naive baseline would be random, which would be 50%. So the baseline in this case would be 50%, we achieve 88.9%, which is quite good. And actually the best score achieved for this dataset without an external dataset and pre-training and all this would be around 95%, which means that, okay, of course we are not very close, but it's not that bad, 88.9. So let's continue to see what we can do to increase this 88.9. One thing that we can do is, as I mentioned before, we still are in the family of bag of words. We still have treat the tokens as just a set, but in this case, we can create either tokens of one word or tokens of two words. For example, this sentence here, the cat sat on the mat, could be this tokenization for bigrams, the word the, and then we have the word cat, and then cat sat, etc. And this somehow, as I mentioned before, gives some information to the model regarding the ordering of the words. It's bigram, it could be trigram to give even more information, but bigram, we will see that it increases. So it actually works. So let's configure the text vectorization class that we created before in order to output bigrams this time. And it's very, very easy. The only thing we have to do is define n grams to be 2. So by default is Unigram. We define 2, and we don't have to change anything else. We just have to, of course, adapt it again. So we call adapt on the text only train dataset, the one that we created before. And of course, we have to map this to so that the datasets actually output the multi-hot for the biogram. After that, we just call get model, model summary, and we're supposed to train. Again, I already trained. So let's see what will be the accuracy for the biogram in comparison to the previous one. It will take some time to create this because biograms take more time. And of course, to build the model and everything, but it's quite fast. And we can see that it's 89.9, so it's quite good. I mean, we increased by 1% just by using bigrams, which is really good. And we will see that it's actually very important. Now, for the moment, we used the multi-hot way of encoding, which means it's either 1 or 0. But 1 can be that this word appeared once, twice, 3 times, 10 times, it doesn't matter, it's still 1. There is another way to encode the information of how often a word appears. For example, any sufficiently long movie review could contain the word terrible, regardless of if it's positive or negative review. But if you see the word terrible many times, it's most likely that it will be a negative review, which means that sometimes this information of how often a word appears is important. So let's see what we can do to configure the text vectorization to get this information. Here, for example, you can see that the word "the" appears 2 times, okay? And this is one way to encode it, is to say that this word appears 2 times, the other words appear 1 time. So in order to do this, we just have to write output mode count in this case. And so this would work maybe, but there is a better way to do it. The problem with this approach is that there are some words, like we saw before, the word "the" or the word "a" is other common words, that will always have a big number there. It will be always many times in a long sentence, a long paragraph, for example. What we want is to normalize this somehow, so that a common word in the corpus will have less weight. And in order to do this, we use the TF-IDF, which is very common. And the letters come from the term frequency inverse document frequency. And what this means is that we have we somehow want to make the words that are common in the corpus to have less weight than the words that are less common. And of course, we take it for the term frequency for the sentence. In order to apply this, we just call output mode TF-IDF. It's again very simple. And now let's see if the TF-IDF bigram model will get any better results. So yeah, I changed this because sometimes it breaks if you don't have enough memory. We don't do something important here. We just adapt the again the text vectorization because now we have the TF-IDF, and then we do the same thing as we did before. We get the model, nothing new here. Let's see now how the evaluation will go for the TF-IDF 2-gram model. I guess it will take some time again to adapt it, but other than that, yeah, it's already adapted. It runs quite fast. So no, it didn't get any, I mean, it actually got slightly worse, but this can be just spurious. So the idea is that it didn't improve this time. So it's not necessarily that if you apply something like this, it will improve. But nevertheless, it's good to test it to see if it gets any better or not. Now, a side note, we will continue with the other methods, but the side note is regarding exporting a model that pre-processes the raw strings. And why this is important? This is important because up to this point, we see that we have a separate function in order to apply all this standardization, the splitting, the indexing, tokenization, all this stuff, the pre-processing. We implement them before the data are fed to the model. But this is not a very good solution if we want something that is standalone. So if we train a model in one environment, a specific programming language, operating system, hardware, whatever, and then we want to implement in another environment, then we have to rewrite all the pre-processing steps again, so that for a raw data that we get, for example, for something on the internet, a chatbot or whatever, to implement it again. A solution would be to have a standalone model that does the pre-processing internally. So this is what we can do. We can do something that takes the raw data, the sentences, we feed the sentences to the model, and then we get the output directly. And in order to do this, it's just 4 lines of code. It's very easy. We define a new input, which will be of shape 1, because without the path size, of course, because this will be the type string. As we saw before, it's just 1. And then we apply the text vectorization, because if you remember, text vectorization is actually can be treated as a Keras layer, which means that we can take this, pass these inputs, and get a symbolic tensor here that we can then feed to the model to take the outputs. And then the inference model can be just this model that takes these raw inputs and returns the output. So this model could be standalone. You can feed it a simple sentence in English and with whatever, actually not even in English, it can treat also other characters because it will remove it, and it can work the same way we saw before. So let's see this. Again, here you see that we feed this sentence without any preprocessing the raw data. Of course, we have this because it still needs a batch. And we feed it to inference model, and we'll have an output, and this will be 85.82% positive. And of course, it's positive based on what we can see here. So this was a side note, but important. I thought that it's good to mention this. Now, we saw the bag of words approach. So again, bag of words, we take the tokens, can be one word, can be bigram, whatever, but we treat them as, we don't care what is the position, we just treat them as a set. Another approach would be to treat the words as a sequence, as I mentioned before, as steps in a sequence, in time series, let's say, example that we saw before. So let's see the first practical example on this. First of all, we want to prepare the data, again, preparing integer sequence datasets. And in this case, we call text vectorization. We define a max length. So this max length will be the maximum length for it, for how many steps we will have in each sample. So how many words, let's say, we will have in each sample paragraph or sentence. And we have the maximum token, so how many will be like the vocabulary before. We feed this information when we create the text vectorization, so maximum tokens. The output mode will still be integer. And we define here the maximum length in the output sequence length. And then we adapt it. We don't change anything here. We just adapt it on the training sentences, and we map this text vectorization on the dataset so that we take the integer train dataset. Now let's see how this works now. So a sequence model built on one-hot encoded vector sequences. Let's see how we can do this. First of all, we define the batch size, and then we create this, which will be, as you can see here, a recurrent network because it has a recurrent layer inside. And we have the input. So here, the input we call batch input shape. You can use this if you know exactly the size of the batch because it's more optimal, it runs faster. So here you define the batch size and you define the maximum, the max length. Of course, this will not be the max, it will be the fixed length in this case, the 600 steps in each sample. And we take these inputs and we feed them to the one hot. So each number in this, so again, this thing, you have the sentence and you have numbers. So the first word is this number, the second word of the sentence, this number. If it's not enough, you have zeros in the end, so that you have 600. If it's more than 600, you truncate, you crop, and you keep only the first 600. So you take these integers now and you make them one hot. And of course, you have to define what is the total, so maximum tokens of 20,000. So you have this, which is the embedded. So this is the one hot for each token for each step of the sequence. And then you have the LSTM with 32 outputs, and you put it inside the bidirectional, so that you have the bidirectional LSTM layer as we saw before. You apply a dropout in the output, and you have a dense layer with sigmoid. So nothing new here. All this, the compilation will be the same. So we have this one, which is again 16 because it's a batch size, 600 because we have 600 tokens, 600 numbers for the length. And then after with the one hot, it's 600 by 20,000. So it's a big thing here. You see that we have 5 million parameters. Now let's see how this will, okay, let's start training. So nothing new here, we just make the checkpoint. I have already trained. This one takes long time to train. Again, this is because it has too many parameters for the LSTM layer. So each word will be 20,000 numbers. And you have 600 words for each sample, for each sentence. And you have many sentences, which means that this is too heavy, and we will see how we can make it shorter actually, so that we gain more information. So one hot is not the best way to encode this kind of information. So let's wait a couple of seconds more and see what will be the accuracy. So naturally, you would expect that now that we use something that is recurrent, and this by default has the information of what is the order of the words would be better. But as we see here, it's actually worse, and it's not just worse, it's worse than the binary 1 gram. I mean, this one, if you remember, was one dense layer and the output. Bag of words, Unigram, it was the completely simple thing that we could do. And this bidirectional LSTM, whatever, is worse. So this is very important, a lesson to start, as I mentioned before many times, and that's it's written in the book, start with the very simple. Don't start with the bidirectional transformer, whatever. Start with something simple, see if it works. If it works, keep it as a baseline, and then start adding stuff. If we had started with this, and this is very slow, again, it took, I don't know, 54 seconds just for the text. So again, the model trains really slowly, and the reason is this, it's because the inputs are very large, it's 600 by 20,000. So you have 20 million floats per movie review. And it performs worse than the very light one that we saw before. And as I mentioned, one hot may not be a good idea, and there is a solution for this. It's the word embeddings. Let's see what this word embeddings is. So the word encoding, one way or the other, since we take the token and we transform it into some kind of array, it is feature engineering. And as a feature engineering, it has some decision making. And this injects some assumptions that we have regarding the structure of the feature space. What does this mean? This means that, for example, for the one hot, the assumption is that every token, the different tokens, are independent from each other, because by default, one hot vectors are orthogonal to each other. So they are all as if they were independent. But it's not true for a real language, right? Because in real language, we have in natural language, we have words like film and movie, which when we encode them, we would expect these encoded vectors to have some geometric relationship to each other, which means that since semantically they are close, we would expect that the distance also geometrically would be smaller than other vectors, which is again not true for the one hot, but we would like it to be true for another way of encoding. And the solution to this is the word embedding. So the idea with word embeddings is that it maps the human language into a structured geometric space instead of the very simplistic one hot. So here is an example. A structured word embedding a Latin space would be something like this. For example, we have the words, the array for dog here. Let's say we have 2 dimensions, the array for wolf here, tiger and cat, which means that we could actually compute something like the petness array. So from pet to wild animal, this would be a vector that you could apply from pet to wild animal, from dog to wolf. And if you would apply something similar to cat, you should go to something like tiger. Or you could have from canine to feline. You have dog, you have this array that leads to cat, you have wolf. This would be something that would lead more or less to something like tiger, which means that there is some structure. You can add or remove some vectors and you get something meaningful. And a very common example is with the gender or the royalty. So you have man, you add the female vector, you end up with human, or you add the royalty vector, you end up to king, again to queen, etc. So this structure, it's not always like this. I mean, of course, here it's a 2D, it's very simplistic, but it actually works. So you can see that you get something similar in well-trained word embeddings. And to see the difference, again, one hot encoding is binary, so either 0 or 1. You don't have intermediate. It's very sparse, so you have only one in many zeros, I don't know, some thousand. It's very high dimension, so the size of your vocabulary. Word embeddings, on the other hand, it's floating points, so you can have gray, you can have 0 point something or whatever. And they are way more low dimensional than the other ones. So you can have usually something like 256 up to 1024. This is usual numbers for word embeddings. And so in order to obtain, so how we actually get these word embeddings, one way would be to learn them jointly with the main task. So we will see how we do this. We start randomly and we have this word embedding layer that is part of the model and it's trained with the model. This is one way. The other way it would be to use pre-trained word embeddings. Now, let's see both of them. So let's first see how we can learn the word embeddings with the embedding layer. So imagine the embedding layer to be more or less some kind of dictionary that maps the integers, the number of the token, to a dense vector. Okay, so the input would be the index of the token, let's say 3, and the output would be a fixed size dense vector, 256, let's say. So this is how it works. We have the word index, we pass it through the embedding layer, and we take the corresponding word vector. So rank 2, batch size, sequence length, and is the input, the output would be batch 3. So batch size, sequence length, and the embedding dimensionality, which is what the recurrent layers expect. And it's very simple to create it. I mean, it's almost annoyingly simple how you can create these things nowadays. Just layers.embedding, you define these two numbers. So how many tokens, 20,000, let's say, what will be the output, 256, and boom, you have the embedding layer. That was all. And in order to use this inside your model, again, it's very, very simple. You just take something that's just a number, so none here, because it's just an integer, and you pass this, again, imagine this as a dictionary that takes this number and returns this 256 vector. And you pass this, so this is what before we had the one hot, now we have the embedding. Same from here afterwards, we have the bidirectional, dropout, dense one output, etc. So this is actually much faster than the previous one. It's still slower than the dense one though. And we will see that, well, we will see it's better or worse. So, yep. Actually, it's worse. It's slightly worse. Well, no, it's worse for some reason. So, and actually, the important thing is that it's not better than a binary Unigram. Okay, so we still haven't go even slightly closer to what we had at the beginning. So one reason for this, what could be wrong? I mean, why this happens, right? So one reason would be that it has partial access to the data, which means that you don't have the whole sentence every time as you had in the Unigram or bigram, the bag of words, because we truncated to each sentence to 600 words, which means that the big ones are you miss some information. Another reason could be the padding. So it's full of zeros. So there are some sentences that are very, very small, let's say 30 characters. So the rest of the up to 600 would be just zeros. And this thing treats them and tries to learn. So this means that the information becomes faints out, the information from the actual sentence, because it has many zeros that it treats again and again. So let's see how we can avoid this, at least the zeros part. So in order to avoid this, we can use the masking. So again, the bidirectional RNN, one of the two unidirectional looks the tokens in their natural order, which means that all the last iterations for the small sentences will be just padding, will be just zeros, and can have hundreds of them, which means that, again, the information fades. One way to avoid this would be masking, which means that we give the information to the model that you should skip these zeros. You should not train on this, iterate on these zeros. And this is what it would look like. So we have the embedding layer. We take this, and let's say we have I cannot show this. So let's say that we have these inputs, okay, here with some padding so that they are the same dimensionality. And we pass these inputs to the embedding layer, this one, and we call compute mask. So this is actually computed internally if we define it. And the compute mask will return something like this, which is true for numbers that are not zeros and false for numbers that are zeros. And this information will be important for the model not to iterate on them. Remember this compute mask because we are actually going to implement it next time. So using the embedding layer with the mask enabled, so the difference is that we change this mask 0 to 2, and all the other things are exactly the same as before. We use the same trained dataset, the same adapted. And so let's see if it will get any better. So the difference now from the previous time is that this doesn't iterate, didn't train on the zeros. It's just past the zeros. And we see that we have something better here, right? So from here to here, it's significant increase. Still, well, it's close to the binary, still not better than the Unigram and way far away from the bigram. So, but still we got better. So this is good. Let's see what else we can do. So as I mentioned before, one way for word embeddings would be to learn them during training. Another way would be to use pre-trained ones. So when we don't have many training data, we can use pre-computed embeddings. And this is more or less what we do with the pre-trained convolution network. We use the weights and then we add the classifier, etc. So there are many sources for embeddings. We will use this time the global vectors for word representation from 2014. And let's see how we can use this. So I have already downloaded in the notebook. You can see how to download this. And the only thing is that we have to create an index, and we take this, we just parse it. It's just that we split it, etc. And the idea is that we make this to a Python dictionary. And let's see what it will look like. I don't know how big this is. Okay, so it has 400,000 word vectors. So we take this thing and we, the way to use it in an embedding layer would be this. So we have the text vectorization that we had before. We get the vocabulary, this thing, and then we have the word index. So we take each word. So this is more or less in order to create a dictionary from the list. Okay, so here it's a list, and then we create a vocabulary. And then what we do is that we create this embedding matrix with zeros, and we have how many tokens we will actually have in this in the embedding dimension. And then we just take the items. So for each word, we see if the word is less than the maximum number of tokens that we want to keep. Then we have the embedding vector from the embedding index, we get this word. And we get because we don't, if we call get, then if this word is not for some reason in the word embedding, the clover, then it will return none. And then if the word is not, if the embedding vector is not known, so this word is actually embedded in this Glover word embeddings, then we just assign to the embedding matrix this. So this process will create this embedding matrix. And then we just have to call the embedding layer. So there is this layers.embedding where we define again these numbers, and we initialize the embeddings with a constant because we want them to be fixed using this embedding matrix. We define it to be not trainable and masks to be 0. So these two blocks is how we take something that is a pre-trained word embeddings, and we create a layers.embedding using this. Now, let's use these embeddings in a model now. So again, we just take the integers here and we pass these integers through the embedding layer. And this will be the pre-trained embeddings from Global. And then the rest of this is more or less what we had before. Let's see if it will get any better. So again, we have So this is the embedding. So the embeddings, you see that it has all these parameters, but they are, of course, non-trainable because we have frozen it. So let's see if it will be better or worse than the pre-trained, than the trained from scratch that we did before. And it has accuracy 87.4, which is actually worse than the ones that we learned by ourselves, right? So it's not necessarily that if you pre-train it, it will be better. And the idea is that for the specific task, we had enough data to actually train it, and we had enough samples to make something that is specialized for this task. So it's not that it's always more helpful. In this case, it was not. But in many cases, it works better, especially if the dataset that you have, the trained dataset, is small enough. Let's summarize to close this session. So as we mentioned before, there are two approaches, two kinds of NLP models. One is the bag of words models, which we don't care about the order, and we use dense layers. The other one is the sequence models, like the RNN that we saw today, or if we could use wanted ConvNet or a transformer, which we'll see next time. And then there are the word embeddings instead of the one-hot embeddings or the multi-hot. We have this, which is vector spaces, where the semantic relationships between the words are modeled as a distance. So the semantic part is modeled as a distance geometric part in the latent space, in the embedding space. So that will be all. Thank you very much.